Hi, my name is Tom and you are at level 27 in Mastering Einstein's Special Relativity. This is the C level. We will dive into time dilation, classic time dilation and real-world time dilation. I'm assuming you've seen levels A and B of 27, but I will do a short recap on those levels before we go into the nitty-gritty. So let's see. Where's my cursor? Here it is. The setup I introduced. We have a house with a clock. We are in the house. We have a train with its clock. It's running at 80% of the speed of light. We have someone in the house watching the clock in the train. We have someone in the train watching the clock in the house. And I did these two animations. The animation is still jumpy. I don't know how to fix this. But here they run. And in this case, they also should end at the same time. But nevertheless, the clock in the house moved 60 seconds. Einstein will tell us that the clock in the train moved 36 seconds. Classic time dilation. Real world time dilation, the telescope will tell us 20. And if we do this the other way around, from the perspective of the train is not moving, he sees the house moving, we see this. We let this run for 36 seconds from the perspective of the train, and then, because now that clock is stationary, the house clock is moving, it will be at 21.6 and the telescope will tell us 12. And we get this incredibly confusing conversation. Like when my clock was at 60, my intuition would tell me your clock is at 60 as well. But Einstein says no, it will be at 36. So I picked up my telescope and I didn't see 36, I saw 20. And then the other researcher says, well, wait a minute, when my clock was at 36, I expected yours to be there as well, but Einstein told me it will be at 21.6, and my telescope told me it was at 12. So you get a really strange conversation between those scientists. They will either have a major science breakthrough or get into a fight, because this is just unreal. Gives you headache. Let's dive in doing the math. Let's first derive classic time dilation from the Lorentz transformation. If you don't know what the Lorentz transformation is, you will have to go to some of the previous levels, but I expect that you have mastered those. I'm introducing my special secret notation again. It's very, very important in special relativity that you know who's talking about what. So I introduced this notation. The x is the location of some event from some perspective. The time of some event from some perspective. The velocity of some observer from some perspective. I also introduce now v prime, which is v over c. Makes it a little bit more easy because then I can also use x over c. And the space-time diagram that I'm going to use later will have x over c on the horizontal and t on the vertical. And if you are new to the scaling of the x, I invite you to look at level 26b, in which I introduce the space-time diagram. T will be this. This is just classic Lorentz transformation. You should be familiar with these equations. Now let's suppose that the event we are going to pick from the perspective of observer 2 is the clock of observer 2. That's always with observer 2. Then we can just punch in for E event the clock of observer 2. So just don't think about it, let go of intuition, just follow the math. Put in E is observer 2 clock. And you get this equation, because that's the Lorentz transformation. If you want to expand that a little bit further, you can fill in what the x-coordinate is of the clock from the perspective of observer 1. And that will be, of course, the velocity of the clock from the perspective of observer 1 times the time of observer 1. And the time of that event through the eyes of observer 1. So we fill in x, and then we simplify a little bit by taking the c's out. We pull t out of the brackets, and we get this equation. And if you look at gamma and you multiply gamma with 1 minus v squared, you get something like 1 over gamma. So here it is, classic time dilation. The time of the clock in the train through the eyes of the person in the train will be the time of the clock in the train through the eyes of observer 1 divided by the Lorentz factor gamma. And because gamma is always bigger than 1, the time in the train will always be less than the time of that clock through the eyes of observer 1. And this is time dilation. Moving clocks tick slower. Let's assume that observer 1 here is stationary. Then the clock of the clock in the train will always be late, right? So this is classic time dilation. We did this derivation, I think, also earlier, somewhere around level 19, I think, with Pythagoras, etc. So you can see it there as well. Cool. I'm a big fan of, well, next to the space-time diagram, I also like event tables. So let's put in these events. Let's say we have 3 events. The house clock is at 60, the train clock is at 36, and the house clock is at 21.6, and fill in the blanks that we already know. So from the house perspective in red and the train perspective in blue. So these are the numbers we know. And then you just let go of your intuition. Do not think this through. Just take the Lorentz transformation, here it is, and calculate the missing cells. And you will get it minus 80, 100 for x and t for event number 1. For event number 2, you will find 40, 80, and 48 and 60. And you will find these numbers for event number 3. And this table is not really intuitive, right? You've applied the math. You've not made, like I did, 100 times mistakes of who's talking about what. So you got this right, but it doesn't really tell you. You want to visualize this. That's always the case. Before we go into the visualization part, let's look at telescope time. Let's look at real world time dilation. And again, I expect you have seen the previous A and B level. So here is our space-time diagram. This is the speed of light. This is the observer, the stationary observer. This is the train running at 80% of the speed of light. And you can write down that the equation for this blue line is the one you see here, right? And in this case, V prime is 0.8. Event number 1. The person in the house looking in his telescope at t is 60 at the clock in the house. Event number 2 is the time and location of the clock in the train. And now we punch in the projection line, with an angle of 45 degrees, in which the light travels from the train back to the telescope in the house. And this line, the black dotted line, has this equation. And now we want to find what are the coordinates of event number 4, because event number 4 is when light started to travel from the train back to the telescope in the house, reaching that telescope at 60 seconds on the clock in the house. That's event number 4. And the X and the T location are here. And you can do this by intersecting the blue line with the black projection line. So it looks a little bit complex, but if you give it a try, I'm sure you can figure out that these are the coordinates of event number 4 through the eyes of observer number 1, the stationary observer. So now let's derive telescope time. I want to know what the time is on the train clock at event number 4, because that's what I will see in my telescope. And that's what I want to know. I want to know the time I see in the telescope when the telescope is at event number 1, so in the house, through the eyes of observer 1. First, we take the Lorentz transformation again. We can write down that the time of event number 4 through the eyes of observer number 2 equals etc. Yeah, you can just fill in the Lorentz transformation. And you see that we made it a function of the time and location of event number 4 through the eyes of observer 1. Well, we just derived the x and the t location of event number 4 through the eyes of observer 1. They are in the graph. So you just take those, fractions and put them in there. Here they are. So you just did some replacement. Now you can make this, let's see what the next step is. Let's begin with the time. The first is the time of event 1 through the eyes of observer 1 is exactly the same time of event number 2 through the eyes of observer 1. So we are replacing t event 1 by t event 2. That's the first replacement. Then in the second part of the equation we see v prime multiplied by t. Vt is just a location, right? So we can fill in, that will be the location of event number 2 through the eyes of observer 1. And if you now look at this equation and you compare that with the first one, you can see that this is the case. The time in the telescope will be the time in the train according to the observer in the train divided by v prime plus 1. So this is what I call the telescope time. It's the dilated time divided by 1 plus v over z, because that was the definition of v prime. So there you go. Now you know how telescope time is derived. Let's apply this for the house. So this was the conversation we had, and you can see that this is the equation we just derived, and you can just punch in the numbers. The time of event number 4 through the eyes of observer. The telescope time is the time of event number 2 through the eyes of observer 2, which will be 36. It will actually be 36 seconds in the clock in the house, and you divide it by 0.8 plus 1 and you will hit 20, which is what we have been talking about all along. We can do it also from the perspective of the train. Again, telescope formula. Be very careful who's talking about what event, from whom's perspective, etc. Punch in the numbers and you will get at the 12 seconds. Still, this is not really intuitive, so if you want to do this intuitively without the math, go back to the B level or visit this link. I will switch my screen to that website as well. Here it is. Here I put in the house in red, the train in blue. I put in the event 60 seconds, 21.1 second, 20 seconds for the train, 36 seconds for the train, 60 seconds, and you can just take your mouse and pull the perspective back and forth. And you can follow the dotted lines, the black dotted lines, which are the projection lines, in which you can actually see light travel from the house to the train. And if you are in the house's perspective, you can see the light travel from the train to the telescope in the house. And by doing this back and forth is like 1,000,000 times more intuitive than doing the math using the equations. But this is what goes on if you do it like this. I hope you enjoyed it and now fully understand that time dilation does not incorporate the fact that light needs time to travel back to the observer. And if you want to do it real time, you have to compensate for that travel time by dividing by 1 plus v over c, or v prime. If you want to see more, these are all the levels I created before we came all the way to this level. These are the first 18. You can pause the video and see if there's something you like. And this is the second batch all the way up to the twin paradox. Next level will be level number 28. This was time dilation. Then we'll do length contraction. Again, A level will be a story, B will be length contraction using the space-time diagram, C will be length contraction doing the mathematics, and we will do classic and real world. And I hope to see you there. Thank you for watching.